So, the schematic is very clear, right. So, same as the gas. So, in this case you can also have a process done in using a shielding gas. Okay. So, in SMAW in most of the cases we do not use shielding, it is all self shielded, whereas in flux core arc welding we can also play around the composition of the flux. In some case, so you want to have a maximum alloying, so you want to reduce the concentration of the flux, especially calcium carbonate for example. So, then the shielding gas which you generate is not sufficient to have a sustained arc. So, this process can also be now shielded by external shielding. Okay. So, in that case, so you can reduce the gas generating compounds from the flux, you can add more amount of alloying elements. Okay. So, in that case your process stability increases, it is similar to GMAW. The advantage is you get the efficiency of GMAW, and you also have advantage of FCAW by having flux, the flux interfering with the droplet transfer, enhancing the kinetics of droplet transfer, also protecting the well pool by the flux, the slag. Yes, it is clear. Okay, we will see one by one when we go further. So, sometimes you may also send the shielding gas, and if you are using a self shielded FCAW, you do not need shielding gas, because flux itself can generate shielding gas, right. It is clear. So, then you have a slag deposited on top of the well pool, and then you can break it after welding. Good. So, this is the cross section of the electrode which you saw in last class as well, right. So, you have an outer shielding and then the flux is inside. Okay. So, now it is almost compacted. So, you can have a look at it, and then so this is 2.4 mm diameter FCAW, it will not come out even if you tap, because it is already compacted, right. So, it is already compacted with the binder. So, all the compounds or the flux are added inside, and then the electrode is made from the flat strip, and then you add the flux powder, and then you close it, and most cases it is not really welded, it is just simple folding, right. So, they just fold it and then they close the seam, and you can generate as much length as possible, and then generally we make it similar to what GMAW electrode filler. So, we will have spools of electrodes made with varying weights and lengths, and that can be fed into the power source. Yes, it is clear. Good. So, typical cross section looks like, so you can make in a seamless tube, right. So, or you also have a butt seam, and this is the electrode I gave you, it is a butt seamed electrode, okay, where you have simple joint, or you can also have a varying joggle seam on the complex section. So, in this case, so you can also improve or increase the amount of alloy molten. So, in this case the cross section of or the length of the metal is much lower than when you have such a geometry. So, if you want to increase the liquid metal droplet, the contribution from the actual metal, so you can also change the sheet geometry in such a way that in this case you melt more metal, and then you have a little amount of flux surrounding the metal sheet. So, these kind of electrodes, the amount of flux which is there, it is not sufficient to produce enough shielding. Okay. So, because here the metal volume is much higher than the flux volume. So, such a geometry, complex section geometry is used with conjunction with the shielding gas. Okay. In most of the cases, self shielded FCAW would have a design of a seamless tube or a butt seamed the electrode. So, for a complex section or joggle seam sectioned the FCW consumable, generally you need to have an extra shielding, because the volume fraction of flux with respect to the metal decreases significantly. So, you need to generate more gas. So, you may have to use an external shielding. Yes, it is clear. So, these are the commonly used the designs for FCW. The one I circulated, it is actually butt seamed FCW consumable. Okay, good. Any questions so far? Move otherwise? Good. So, the melting rate. In GMAW, what is melting rate? So, this goes away, right? In GMAW, the melting rate of the consumable is alpha times I beta L I square by A. What is L here? What is L? Stick out length. Exactly. So, you have an electrode tube, contact tube, okay, and then so you have an electrode coming in forms an arc, isn't it? And this is stick out length L. Okay, so this distance, what is this distance? This is contact tip, and this is workpiece, isn't it? Then what is this distance? This is contact tip to workplace distance. Okay, it is very simple. So, CTWD, that is what we define all the time. CTWD minus arc length is your stick out length, right. So, CTWD defines the distance between the contact tip to the workplace, and that is a very important parameter, right. So, CTWD is an important parameter, because that would determine the stick out length and the arc length. Okay, if you are doing in a constant arc length case at a given CTWD, then your L should be based on your melting rate, isn't it? So, in a conventional GMAW, so we use an I plus I square relationship, whereas in this case we also have to have another term, because the heat is also consumed by the flux, isn't it? So, when we did the heat balance to calculate the melting rate, right. So, we looked at 4 important parameters, isn't it? When if a consumable is an anode, okay, the heat generated in the anode, so that is QA, isn't it, plus latent heat of melting, right, and then heat generated in the anode by resistance heating, and then the heat needed to increase the temperature of droplet to the droplet temperature. Okay, that is the heat balance we did it to calculate the melting rate, right. Apart from these 4, there is another factor here when you use the consumable welding. Which factor is that? So, heat absorbed or heats eaten away by the flux, right. So, there is another component comes in when you are doing a mass balance or heat balance, is the K factor. So, that factor governs the heat consumed by the flux. So, again that is a function of the composition of the flux, whether you have a rutile based or a basic flux or cellulosic material. So, again as a function of stick out length, we can also calculate the wire speed rate. So, if you increase stick out length, what happens to melting rate? So, if you increase stick out length, for example 25 mm for a given current on 150 amperes, stick out length increases means melting rate also increases, isn't it? So, this is the low stick out length 5 mm and this is 25 mm, isn't it? So, this is 5 mm. So, at 150 amperage you are welding of an 2.4 mm flux core arc welding. Just by changing stick out length, you can almost double the melting rate, okay, isn't it? From 4 mm per minute to 8 mm per minute, it is almost doubled, isn't it? But current is same. Current is same. So, why the melting rate is changing? See, if the current is the same, your question is why does melting rate increase? Look at this equation. If stick-out length changes, melting rate increases. Okay, because the more the length, the more Joule heating. Okay, so you looked at Joule heating, right? So, what is Joule heating formula? I square R, okay, rho L by pi R square I square, isn't it? So, that is how we derive the melting rate equation by heat balance, isn't it? So, what is L here? L is this stick out length. So, more the stick out length, more Joule heating, then more heat is there for melting, right. So, it is again the heat balance what we derived. So, by just changing the stick out length, you see that already the melting rate can be doubled, right. So, that is what by all other parameters in this equation are fixed, that is why we take it as a constant, because the process efficiency is depending on the sealing gas, the characteristic of the ionization, the reactions, the heat generation which is happening. That is what the equation first time I derived, right, the electrical resistivity of an arc. Okay, that is determined by the arc characteristics, right. So, that is fixed for a given process, for given shielding conditions and given polarity. Okay, so, what are the factors you can influence apart from that is your composition. So, composition is fixed. If composition is changing, latent heat of melting is changing, right, and then H is changing, and then you also change Cp, specific heat capacity. When Cp changes, then you also change the heat required to increase the temperature of the droplet. So, now you fix the process, you fix the chemistry, and what are the parameters you can contribute. Okay. So, in this QA term, the only parameter which is changed irrespective of process and the composition is current. Okay. So, the current can be changed. Okay. In the resistance heating part and Joule heating part, there are two other parameters, is the diameter and the length. Okay. So, you fix a diameter for a given well diameter, consumable diameter. So, what other factors can be changed? The length, right. The length is stick out length L, right. So, two parameters independently can change by fixing everything. Say suppose that is why it is called independent parameters, because that can also change person to person. So, you weld today morning and next guy comes and welds, and if he changes stick out length, everything is the same, shielding is same, the process is the same, right, material is the same, diameter is the same. Even if you fix the current, if you change the stick out length, then melting rate change, right, it is clear. So, this graph shows in FCAW by changing the stick out length, you can almost double the melting rate. Yes, it is clear. Okay, good. So, the K factor takes care of the heat consumed by the flux by decomposition to generate hydrogen, the gases, carbon dioxide, there is other shielding gases. Good. So, the main reactions for shielding gas generation in these flux coated electrodes or FCAW electrodes is a calcium carbonate burning into calcium oxide and CO2, and calcium oxide forms a slag and CO2 is a shielding gas. Okay. So, in cellulosic material the fluxes carbon monoxide and carbon dioxide and also the hydrogen. Okay. So, cellulosic material they contain titanium oxide, it also generates hydrogen. In rotile based fluxes, the main shielding gas is hydrogen, because titanium oxide can effectively reduce the water into hydrogen and oxygen flux. Okay. So, that is why the titanium oxide nowadays is very commonly explored by the nano guys to generate hydrogen by photocatalytic. So, nano titanium oxide rutile used as a catalyst to decompose water into hydrogen and oxygen, because titanium oxide has a photocatalytic effect. So, when the water droplet comes to the surface of the titanium oxide, it promotes the disintegration of water into hydrogen into oxygen. Okay. So, titanium oxide nowadays people explore left and right, generate the nano titanium oxide, use it as a photocatalytic agent to generate hydrogen. So, hydrogen fuel cells, you may see they use nano titanium oxide rutile, and we use it in welding also, but we do not really call ourselves nano guys, because ultimately when titanium oxide is added in the flux, it would disintegrate, it becomes nano titanium oxide, and we generate hydrogen, right. That is why I call welding, welding does everything. Okay. So, we make steel making, we also work on hydrogen generation, right. So, but it has been done for several years, and we do not claim ourselves as an advanced researchers. So, we play low level, okay, but still we use the titanium oxide to generate hydrogen for shielding, right. So, these three are the major reactions that are happening to generate shielding gas. So, if you reduce the flux concentration, increase the metal volume fraction, then you need to use some shielding. Okay. So, in self-shielding self-shielded electrodes, we do not need external shielding, because the flux decomposes and generates enough shielding gas for arcing, right. It is clear? Good. So, we move on. So, I just put 4 important roles of fluxes in the SMAW and FCAW. The main important function is obviously it should generate shielding gas, right. So, either be carbon monoxide or carbon dioxide or hydrogen. So, that is the main function, to generate shielding gas, and apart from this there are some secondary functions these fluxes do. They act as a deoxidizer for the well pool, okay, and they also denitrify and cleans the well pool, and you can also have a dephosphorization, desulfurization done by adding elements which promote deoxidization, denitrization, desulfurization or dephosphorization, okay. So, to clean the well pool, and then to improve the arc stability, because we know that the oxides have very low ionization potential. So, they also promote ionization. So, if you improve the ionization, so obviously arc stability increases. Again, ultimately the basic definition of arc is sustained discharge. So, discharge is sustained to have a stable arc. So, if you promote ionization by adding oxides, so arc stability increases automatically. Of course, these fluxes can also be added to change the alloy composition of the element. Okay. So, you can also add precipitation inducing elements like ferro-niobium, ferro-titanium in steels, and you can also act as a grind refining elements in the fluxes. So, these are all the secondary functions, but the primary functions in these processes to generate shielding gas, right. Good. So, what are types of the commonly used flux core arc welding electrodes? So, I said for plain carbon steels, so we have rutile. So, if you use rutile, obviously if you do not have enough flux to generate shielding gas, you need external shielding. So, rutile the electrodes with the gas shielded. So, that means that you need to have an argon cylinder if you want to use an argon. So, then it becomes argon plus hydrogen shielding, is not it, right, because rutile can generate hydrogen, and then argon can come from the bottle, and then the shielding would be from argon plus hydrogen, right. The basic gas shielding will be argon plus CO2, right. And in SMAW, so most of the cases argon plus CO2, right. It's because in most cases you will have a calcium carbonate fluxes. So, you will have an argon and external shielding and then CO2 generated from the burning of the flux. In self shielded electrodes which I circulated, this is self shielded electrode. So, where you have a maximum amount of flux generated, maximum amount of gas generated by the decomposition of the flux, right. So, we do not use any extra shielding for the electrode I just sent around, because this electrode is self shielded, where the flux inside the core of this electrode burns and generates carbon dioxide. So, this is self shielded carbon dioxide electrode, and you can see the video, the process when we welded this electrode. So, this is the electrode which I sent around, okay, and you see the metal droplet formed, and most of the cases the droplet transfer is repelled globular. So, the flux burns and generate the required shielding gas. You see the disintegration of flux, right. The flux actually goes in and then it burns and generates the shielding gas required. So, these are the fumes that are generated by the burning of flux, and sometimes you may also have, if you have a metal added in the flux, and you also have a vaporization of metals. For example, if you look at these fumes over here, so suppose if you have a ferrochromium added, suppose some guy wanted to, I want a chromium in the well metal, okay. So, you need to add chromium, ferrochromium. When ferrochromium burns, and it can also generate ferrochromium, the hexavalent chromium vapors. So, the amount of vapor you generate by burning these fumes are huge, okay. So, these kind of carcinogenic fumes are very bad for the welder's health. So, generally the flux burns and generate the shielding gas. In this case, the self shielded FCAW, the electrode, where carbon dioxide is generated as an arcing gas. So, you see that this is a basic electrode. That means that there is no titanium oxide. You see the electrode, the droplet diameter, it can go as high as double the size of the electrode diameter, isn't it? So, the droplet is still intact, sticking to the electrode tip. It is highly viscous. The surface tension still keeps the electrode intact to the tip. So, if you add some amount of titanium oxide, the droplet detachment can be promoted, because titanium oxide is known to reduce surface tension, right. So, in this case you see that, so droplet is still attached. Can you see the droplet? So, now it is masked by the arc. Yeah, see the droplet is attached by the surface tension, right. Can you see that? So, this is the droplet and this is the filler, and the arc is there generated by the burning of the flux, and this molten droplet is exposed to the atmosphere, and during this process the molten droplet also vaporizes. So, that is you generate the fumes, right. So, now this electrode, if it contains slightly high amount of titanium oxide or some fluxes which can reduce the surface tension, then droplet diameter can be smaller and it can be detached easily. So, that is the role of the fluxes, okay. So, in this self shielded electrode, which is primarily a calcium carbonate based, you see that it is still attached and we are burning for quite some time. So, I do not know if this video may contain yeah. So, now it is almost like a dip transfer, it is still attached, see that, and its diameter is more than 5 mm. So, finally, it goes into the pool by the dip transfer. right. So, another video you see that clearly. So, it is almost like a dip transfer. Yeah, you see that surface tension. Yeah. See, it goes up even, it does not want to go down, right. So, because of the highly viscous liquid which is there. So, this Doppler transfer can be changed by changing the flux composition. So, these are commonly used the electrode types: rutile, basic, self shielded, and self shielded also basic, but in basic electrode the volume fraction of the alloy, the metal wire, is much higher than the self shielded. Okay. And the electrodes which are used for hot facing and stainless steel, they are all mostly rutile based electrodes. Okay. So, rutile based electrodes are commonly used for hot facing and surfacing alloys because of improved process stability, and you can also use hydrogen as a shielding for stainless steel, isn't it. So, the austenitic stainless steels, they do not have an embrittlement problem. Good. Any questions so far? Then we will move on to the metal transfer in this process, in this case. So, in the most of the rutile based electrodes, the metal transfer is same as GMAW, because rutile reduces surface tension. So, the droplet can be transferred with smaller diameter, right, and you also have a free flight transfer, and you have a rutile based transfer, rutile based electrode transfer, and you will have a simple free flight droplet transfer, and the droplet diameter can be much smaller, because titanium oxide favorably change the surface tension, and that improves the transfer characteristics, right. So, this is the similar, say a simple schematic. Professor John Norrish is given in this book. So, where a rutile electrode promotes the droplet transfer characteristic with much smaller diameter by influencing the surface tension. The video I showed you, that is not rutile electrode, that is self shielded the electrode, where the droplet is not transferred at all. I mean, for keeping longer time, droplet is still intact. Okay. So, by just throwing some titanium oxide, and we can promote the droplet transfer much more effectively by changing surface tension, right. It is clear. So, in the basic steel electrode, that is what you showed you. So, in most of the cases, the droplet would be attached. So, and then you would start striking an arc between the droplet, and then you still have a finger developed by the molten fluxes attached to the electrode, and which is commonly seen. So, you will have repelled the transfer, and then a finger pattern develops at the electrode tip by the molten fluxes, and by the decreasing by the surface tension, the molten droplet would be sticking to the electrode tip and forming a repelled globular transfer. Yes, in a basic gas shielded flux cooled arc welding. Again, self shielding, it increases even further, like I showed you in the video, in the second video. The predominant the transfer mechanism is a repelled globular, right. So, you want to see the video again, you see that. So, this the electrode becomes, you see that repelled mode, the transfer. So, this is the tip of the electrode, and this is the contact tip, and this is the stick out length, right. Yeah. So, you see that upon increasing in size, you also establish and start circuiting and dip transfer. The moment dip transfer happens because of increasing Lorentz force, and this would explode. Yeah, so now it is exploding. You see this? You see the explosion? Yes? See, because of the explosion, it is also still pushed up, and the surface tension is so strong, it keeps the droplet attached to the electrode surface. Yeah, it's clear. So, this is most commonly observed in self-shielded FCW or self-shielded MMAW electrodes, where the droplet transfer is always rippled globular because of the increased surface tension. Yes, it's clear. So, this is a graph showing the droplet volume versus current in FCW and MMAW. So, metal core electrodes, MMA electrodes, and this is rutile and basic, and you see that in rutile based electrodes the droplet diameter is always smaller at any case, isn't it? This is a current and this is electrode diameter. You see that for a given current, the rutile based electrode will always transfer in smaller diameter. Why? Yeah, TiO2 surface tension. Okay, so you always have a smaller diameter transferred in rutile based electrode, whereas in basic and metal core, obviously this also contains basic fluxes, where in basic fluxes the droplet diameter will always be higher. Yes, it's clear.
Then what needs to be done?
You need to be done. We see you can't add titanium oxide to this, so then you will also generate hydrogen, right? So we can think about adding some other fluxes which can favorably change the surface tension. For example, fluorides. Okay, so fluorides or silicates that can be added. But then if you add fluorides and silicates, there are other complications. So now you have to play around with the flux chemistry. So you can think about adding titanium oxide, but the hydrogen should be pinned by some other elements, like for example boron. Okay, so we can also form boron hydrides. It can be removed as a slag. So then the systematic studies should be done to achieve the required droplet transfer. So if once you understand the science behind the process, then we can tackle very common day-to-day problems. Right. So it's clear. The rutile based consumables always give a smaller droplet diameter because of the reduction in surface tension of the droplet. Okay. So what are limitations of FCW? The cost of the consumables, as I said in last class, the consumables are much more expensive than the wire. Although if you look at the actual investment you put up in a factory to make these electrodes are much reasonably small, but the flux compositions, the work you do to achieve the composition and then generate the electrodes with the flux coating or the flux cored arc weld electrodes, and it makes the consumable expensive compared to GMAW, right. And the other the important disadvantage is fume generation by the burning of the fluxes and then ferroalloys you have in flux, and then consistency of the consumables, that is also problematic because the achieving a uniform flux coating is also very tricky. These are powder based, you will have to mix it with binder and then deposit. You need to achieve a homogeneous mixing of the fluxes, the ingredients in the fluxes. So you always have some difference in consistency across the length of the electrodes, right. So these are some disadvantages, but this can be overcome by the advantages of the process. For example, if you look at the overall cost comparison between GMAW and FCAW, GMAW is gas metal arc welding and this is flux cored arc welding. the consumable is always 3 times higher in the flux core arc welding or in SMAW, the cost, right. But you overcome that by other factors. For example, you do not need shielding gas if you use self shielded the electrodes, right, or even if you use a rutile based electrode, the shielding gas necessary is much less than what you need for GMAW. Okay. And then you also have an improved efficiency from the process. So, you need less power, and also the shielding gas which you use also ionize much more lower temperatures. And of course, in GMAW it is more laborious. The consumable is almost 3 times expensive. So, if you add all these costs together, these FCAW and MMAWs are much more cheaper than the GMAW, right. It is clear? Okay, good. Any questions so far? Otherwise, we can see whether we can go to the next chapter.